Yeah. So hello everyone. So today we have Anish Shah with us. He's an analog engineer at TI, and we both are NCC in TI only. And yeah, and he has secured only rank 170 in GATE 2022 in electrical branch. So today he'll be giving a mock interview to me, and it will help you to help you to know how one should answer a question or how one should approach a question. So we'll be starting now. I'll be just putting some question in front of you and he'll be showing me the waveforms and everything I asked. Okay, so let's start. Yeah, so the first question from my side is that this is a capacitor I am having, a resistor I am having, and one more capacitor I am having. Okay, and let's say I have applied a voltage input here. Okay, let's call it 5 UT. Okay, so
Okay.
can you draw the current waveform through this capacitor? Let's call this current as IC1. So can you draw
Okay.
the IC1?
Okay. So like first, if I observe this circuit, right? Look, if I check this, so the voltage across this C and C will be same if we like short the input. So this will be a first order circuit, right? So as the voltages across them are dependent on each other. So that's the first thing. Next, if I just plot the output voltage, that will be more easier for me to analyze. So what will happen is initially it will have some 5 volts across both of these caps, right? Because what will happen, the initial voltages are 0 across these caps, right?
Yeah.
Yeah. So if the initial voltage is 0, so the caps will try to keep the voltage at 0 because the cap doesn't change its voltage instantaneously. As this voltage is 0, hence the current through this resistor will be 0 amps, right? And the voltage across is 0. Hence the whole 5 volt will be applied across these two caps. The equivalent circuit will look something like this. Now what will happen is as the instantaneously the voltage is changing across this, an impulse current will flow through this both of this cap, right? So in this case, the caps will change its voltage instantaneously. So in this case, what will happen is basically what will be the voltage across this? It will get divided into both of them because both of them are C and C. As the charge through them is same, so voltage is inversely proportional to the charge. So what will happen is the voltage across the V naught at t equal to 0 plus will be 2.5 volts, right?
Okay.
Now at steady state, what will happen, both of these caps will have 0 current through them because at steady state the change in voltage will be 0. So the circuit will look something like this, right? Yeah, this is R, current is 0 through here and current is 0 through here. This is t equals to infinity, right, at steady state, and this is the V. So the current is flowing 0 here and 0 here, so current through this also will be 0. So this whole VI will come across this one, right? As the drop through this is 0. So V naught is equal to VI, which is in our case 5 volts. So initially the voltage was 2.5. It was sudden jump. Then we got the final voltage as 5 volts. So the voltage waveform will look something like this.
No, actually, I don't need V naught waveform.
Okay.
So I need the IC current only, IC1 current only.
Okay, for finding the IC1 current, so if I draw the voltage waveform, then I think it will be a bit easier for me to analyze because with caps,
Okay.
we
Okay.
generally, okay, yeah.
Okay. Okay.
So if I draw the V naught waveform, right? So the V naught waveform will be sudden jump here, 2.5 volts from 0. Then it will get charged to 5 volts, right? This is V naught. Now plotting the IC1 will be easier for me because what is happening initially, as I told you, right? An impulse current will be flowing through this. Both of these cap, right? So this IC1 will also contribute to that impulse current. So what is happening, this cap, so basically writing the equation, IC is equal to C dVc by dt, right? So what is happening, so initially the voltage across this cap is coming to be 2.5 volts, right? So if you differentiate this 2.5 u of t, with dt, we will get something C into 2.5 del of t, right?
Okay.
This is the current basically, initial.
Okay.
So the initial current is 2.5 C into del of t. So there will be some impulse initially.
Okay.
So if I draw this, right, this is t and this will be the impulse C into 2.5 del of t. This is the
Okay.
initial current. Okay.
Okay.
So after that, what will happen is, like, this cap has been charged to 2.5 volts, right? Now it will try to discharge through this resistor as it has no path other than this, right? So what will happen in this circuit is this 5 volt will charge this cap, because at steady state this cap is getting to 5 volts, and this cap will discharge through this resistor. So
Okay.
the current will get reduced. So like here the current direction is given as this from left to right, right? For in our case, the current will flow from here. This initially the current will be here, the impulse
Okay.
current,
Okay.
but then the
Okay.
direction will get changed. So as we
Okay.
know, like the what is the voltage across the R at t equals to 0 plus, right? It is basically 2.5 volts, right? Because both of them are dividing equally. So what is the current through this resistor? It is basically 2.5 by R through this resistor, right? And this current is coming over here, and like the current, what is the current through this resistor? So the basically the current through this resistor at t equals to like 0 plus is basically 0, right? I mean, like going in the right direction here, like, or
No. At t equals to 0 plus, yeah, just think. Like, just a minute. Like, this is
yeah,
2.5 by R. It can't be 0. If it is 0, it is a steady state only, right? You have
yeah,
2.5 by R
that is, yeah,
and you have two equal resistance path. So now, what will be the current in this direction?
yeah. So yeah, we have, yeah, this is this cap and this cap, yeah, it's getting divided into two equal paths. So what will happen is this will be 1.25 by R, and this current will also be 1.25 by R, right?
Yeah.
So both of them will get equally distributed, because like
Yeah.
like impedance whatever it is saying is equal across both of this.
Yeah.
So some negative current will come, which is minus 1.25 by R, right? Now after
Okay.
that, what will happen is basically at steady state, uh, like it is discharging exponentially. So this will discharge to 0 volt at steady state. And like the time constant of the circuit is basically, I told you earlier also. So this both of these C are coming in parallel. So that will become 2C, and equivalent resistance is R. So time constant tau will be 2CR of the circuit.
Okay. Okay. Yeah. Great. So basically, first an impulse, then at t equals to 0 plus, the current changes immediately and then goes to
Yeah,
0.
0.
Right?
Yeah,
Yeah, it's a very interesting output waveform, right?
yeah, yeah.
Yeah. So let's remove it off. Okay.
Okay.
Get
Wait.
everything from your
Wait.
side. Like,
We
don't
can
give.
like use a new page actually.
How can I use a new
Wait.
page?
Can you just
Yeah.
see the new page? Yeah.
No, like there is no option from my side actually.
Okay. Okay.
Okay, yeah, yeah. Let's make the circuit once again. I need to ask you more question on the same circuit.
Okay.
So now for the same circuit, you tell me the location of poles and zeros, but intuitively, okay? Not by
Okay.
writing questions or anything. Okay. Tell me the location of pole first.
So the poles, like we know, it's basically the negative of inverse of time constant, right? Basically omega p. Now, as this is like first order circuit, we have already calculated the time constant, which is basically 2 RC. The pole will be minus 1 by 2 RC, right?
Now
Now for
coming to
zeros,
zero.
right? Yeah, coming to zero, like if we see, like if this impedance we make it 0, like at s equals to infinity. If this goes to 0, then this also goes to 0, right? Then that won't give us any 0.
Okay.
But if I see, like if we break the link between this one, right? If we make, like, this is the parallel combination of C and R. So if the denominator becomes 0, then we can get a 0, right? So here, if RCS plus 1 equals to 0, right? Then we will get a 0. So
But
S
we're
equals
getting
to,
this RCS plus 1 equals to 0.
so
I'm not able.
basically this is a parallel combination, right? So we can write it as 1 by CS into R divided
Okay.
by
Okay.
R
Fine.
plus,
Fine. Fine.
yeah,
Fine. Fine. Yeah.
Yeah. So if I write it as like this, the denominator will be this one. Now, if you make this 0, so this will become infinity. We will break the link between VO and VI. So whole current will flow 0, and the output voltage will become 0 also, right? So S will be equal to minus 1 by RC. So in this case, our omega Z will be minus 1 by RC.
Okay, great. So now can you write down the transfer function?
Okay. So first, like for writing the transfer function, we have to like the transformation will be in something this kind of a nature. So this will be the DC again, right? Now
Okay.
it will have some 0, 1 plus omega Z, tau Z, sorry, 1 plus omega Z.
No need to write it like this. Just write down the transfer function. That's all I need.
Okay, okay.
You
So
can do
that
it in
what is
rough
the
as well. Okay, if you feel like doing in rough, you can do it in rough as well, and then simply write the like
okay?
output.
First, like the DC gain is basically half in this circuit, right? Because like at S equal to infinity, no, sorry, DC gain isn't half. Sorry. So at S equals to 0, right? This cap
Yeah.
will be 0. Open circuit. Now this equivalent circuit will be something look like this. So basically, no current will be flowing through here. So VI will be equal to V naught, right? No current is flowing through here. So DC gain is basically 1 for this case. Basically, the like transformation will look something like this. This and omega and plus 1 plus omega. Sorry, this will be divided by omega.
Where are you writing it? Actually, I'm not. Just
You are
can
not
you
able to see.
write on the left portion because
Yeah. Wait. I'm writing on the left. This will
yeah.
be S by omega Z.
No, just write down the expression. No, like you know, don't need to write it like 1 by SY. You have already found the values, right?
0. Okay, you want me to write like that? Okay,
Yeah.
fine. It will be 1 by so RC.
Yeah.
Is it
So
fine?
that will be your transfer function, right?
Yeah.
Yeah. So let's remove it off.
Okay. Let's go to the next one. Yeah.
Yeah. So this is the final transfer function that we got. 1 plus SRC upon 1 plus 2
2
SRC,
SRC.
right?
Yeah.
Now draw the body plot. At once you will plot the body magnitude plot and then you will plot the phase plot. So first let's plot body magnitude plot. Okay.
Okay. So here, if we draw the first body magnitude plot, like, so this will be the magnitude of J of omega. Can you see the screen?
Yeah. Yeah, I can.
Yeah. So this is somewhere like here. The DC gain is 0. So the body plot will start from this point, right? Now where is the first pole or 0 is it coming? We have to check. So the pole was minus 2 by RC. 0 was minus 1 by RC. So the pole comes up first. So as pole comes up first, this is minus 2 by RC. So we'll get a like negative slope of minus 20 dB per decade. Then after like twice of this at minus 1 by RC, the slope will get plus 20. So we had already minus 20 slope. So at that point, it will get to like some constant value because the slope will be 0 at this
Okay.
region, right? After this minus 1 by RC. So that will
What will be
basically be
that
the
value? What will be that value? This value.
this value, right? So for calculating this value, what we have to do is we are going half in this length.
No,
Just think
like at omega goes to infinity.
okay, yeah, at omega equals to infinity, the gain will basically be 1 by 2, right?
Yeah.
So if you take the 20 log 10 dB of this, we'll get the value at this point.
Fine. Now let's draw the phase plot.
Okay, let's go to the new page. Let me write the transfer function for this, right?
Yeah, I will write it down. I will write it down.
Okay.
1 plus SRC upon 1 plus 2 SRC. Take your time. Okay. Draw the phase plot.
Okay, for like calculating the body phase plot, right? So
Body phase plot you are drawing. Okay. Not the exact
yeah.
one. Body phase plot.
Okay. So here like if we like drawing it at once will be difficult. If we like separate this out, right? Just for calculating for the 0 part at first, if you do that,
I am not
it
getting
is
it. Sorry.
So if I just calculate for this part, right, calculating both of this instantaneously will be a bit messy. So if I just first calculate for this part and then for this part, then add those two, then I will get the angle, because what is this? This is basically tan inverse omega RC minus tan inverse 2 omega RC, right? So if I plot for this part, then I plot for this part, then I add these two, then I will get the answer, right? For the border plot, is it?
You will add these two or you will subtract these two?
So basically, I am already getting the magnitude with this. I mean, I'm taking the negative sign with
Okay.
that pole. Right?
Okay.
Yeah.
Okay. Then it's fine. Yeah.
Okay. So first, what will happen is for this part, right? When that h dash of omega is basically equals to 1 plus SRC.
Okay.
We have one like corner frequency at minus 1 by RC, right? Minus 1 by RC. So initially, what was there? Initially, the angle was 0. So what is how do you plot what a phase plot is? Like before this corner frequency, before this decade, so something minus 1 by 10 RC, and after 10 times of this corner frequency, 10 by RC, like the Bode phase plot starts, right? It has a slope of 45 degrees. If it has 0, it is positive 45, and negative if it's pole.
Yeah.
So before this like 10, so we will have one slope with plus 45 degrees, right? Plus 45 degrees per decade.
Okay.
Now at this point, we will have the value at the corner frequency. We will have the phase of 45 degrees, right? And it will go on till 10 minus 10 by RC. Then the slope will be 0, and it will saturate. Here the angle will be 90 degrees. Okay.
Yeah.
This is for the first case. Now for the second case, right?
Now we will draw for the second case.
Okay.
So you are counting it as 1 by 2 SRC, right? 1 by 1 plus 2 SRC.
Yeah. We are plotting like here the h double dash of j omega is basically 1 by 2 SRC. 1 plus 2 SRC. Okay.
Yeah.
Is it fine? Okay. So here what will happen is initially up until we have one corner frequency at minus 1 by 2 RC, right? Now 10 times before this and 10 times after this, we'll start our plot. So 10 times before this minus 20 RC, and this is 5 by RC, right?
Yeah. Okay.
Now up until this point,
like if you are drawing the body plot, like this should be positive only, right? The frequency component should be positive only.
Oh, yeah. Sorry. Yeah. Sorry.
Okay. Yeah. No problem with that.
Yeah. For that one. Yeah. So if you like draw for this one, right? Now here we have a negative slope of minus 45 degrees per decade. Now here at this corner frequency, our angle will be minus 45 degrees. It will go on till this 5 by RC. Then the slope will be 0, and the angle at this point is basically minus 90 degrees, right?
Like, can you explain me like why do you taking the slope after the times of that to be 0?
So
like here your angle is minus 45. That is understandable. That if you put it here, you will get minus 45 degrees, right?
Yeah.
But after 10 times of that, why are you taking the slope to be 0?
Okay, the slope is minus 45 per decade, right? That's why.
Yeah, but after 5 by RC, your slope goes to 0, right?
Yeah.
So why so?
Slope goes to 0 because it settles to that value, right? Minus 90 degrees at pole. At omega equals to infinity, the angle is minus 90 degrees, right?
Yeah.
Am I correct?
So like it's kind of approximate plot that you are saying, right? Because it would be if you put omega goes to 5 by RC, so it would be like 10 inverse 10. So that would be a very large value.
Very large value, and it will be almost like closer to
90.
Yeah.
Right?
Almost closer to, but it won't be exactly, but it will be much closer to minus 90 degrees, right?
Yeah. Okay. Fine.
Okay. So now, like if we add these two plots, right? So adding these two plots.
Add these two plots.
Yeah.
Not an easy task to do, I guess.
Yeah. So that's why, like, if we would have done it like in a single plot, it will be a bit difficult to like calculate the slope and all. So we'll have these points. This is 1 by 20 RC. This is 1 by 10 RC. This is 1 by 2 RC. This is 1 by RC. This is 5 by RC, and this is 10 by RC, right? Now, like between 0 to 20 by RC, what is happening? This is the angle of actual transfer function. Now, omega. So between 0 to 20 by RC, this is 0 and everything is 0. So it will remain at 0 between 0 to 20 by RC, right? 1 by 20 RC. Now, after 1 by 20 RC, and like this has a negative slope of minus 45 degrees, right? Minus 45 degree per decade, but this is remaining 0, right? Up until
Okay.
10 by 1 by 10 RC. So
Okay.
this will have a slope of minus 45 degrees, right? This will have one slope of minus 45 degree per decade. Now at 10 by RC, right? At 10 by RC, this is has some positive slope of plus 45 degree per decade, but this has the same slope, right? So what is happening? The slope are getting cancelled out, and we are having some constant value up until 1 by 2 RC.
Yeah.
Now, like after 1 by 2 RC, what is happening here? 1 by 2 by RC, and like we are between 1 by 2 RC and 1 by RC, right? So again the slope is constant. So up until 1 by 2 RC also the slope is constant. Like now from 5 by RC, right? Here the slope is getting 0, but here we still have some positive slope. So it will still have some positive slope, right? And it will go until like this part only, because we know like at omega is equals to infinity, the like angle of this is 0. Overall angle of this is 0, right? So that's why it will go till here. Yeah, then it will go to 0 and it will continue on for that.
Yeah. So basically these two are the point. This is this 1 point, 1 by 20 RC, right? And then 1 by 10 RC, and then 1 by
1 by 2 RC.
1 by RC.
This is
Yeah,
yeah.
Here the slope is not getting changed, and then the slope is getting changed at 5 by RC.
5 by
These
RC.
are the
Yes, there are 4 points. Yeah, these are 4 points.
Yeah, greatly explained. Yeah, that's a very nice concept. Actually, on YouTube you wouldn't find it much often. So yeah, it's a good concept.
No, I actually saw one of your videos on Bodeblot. Actually, that's where like a bit of like
no,
which pool comes.
I haven't taught phase flow.
Yeah, you haven't taught this one. Yeah, you haven't taught this one. Yeah.
Yeah, so in like the audience will be benefited from this, I guess. Yeah, so let's move on to the next question. Let's clear it off.
Okay.
Or
Yeah. Yeah.
Yeah. One really basic question. Okay. You are flexing your TI bottle, I guess.
No, actually, I was very thirsty. That's why.
Okay, so tell me the current in this resistor.
Okay, so the current in this resistor, right? So like first what I can do is like when I think of current through a resistor, I think of like Thevenin like equivalent. So if I like draw the Thevenin equivalent circuit of this, first if I calculate the RTH of this, right? Like how will I calculate? I will short the independent sources, right? Then I will ground this. Now I will short also this, but there is some resistor here, R and R, and this is R and R, right? And these are my 2 points through which I'm giving one V test and calculating the I test, right? Now V test by I test will be equals to RTH. So here, like what is happening here, we're providing one V test, so this I test is dividing in these 2 parts, and like here what is happening, like this is an loop, right? So no current is flowing through in this, right? Because this is a loop. So the current through this is 0 amps. So if this is 0 amps, so the like current leaving through this like V test will be 0, right?
Okay.
So I think here, I think the RTH will be infinite, is it?
Yeah, it would be infinite. Yeah, that's a very good method actually. I solved it by some other method actually. Yeah, that's a very good method. I actually solved it by current.
So like a similar type of question came in my interview, so I solved it like this only. Okay, so here, like if the RTH is infinity, then what will happen? Basically, we have this equivalent VTH and this R, right, and RTH. So if
that
this
in which
RTH
case
is
current
infinity,
would be zero. Yeah, that's understandable.
current will be zero. I will be zero. Yeah.
Yeah. So I solved it by some other method that I have solved on YouTube as well. So I won't explain it here. But that's a very good approach. Every time if you need to find a current in any resistance or anything like that, just find the equivalent across that. Then you will get to know, right? And like if there was ground on this side, the RT wouldn't have been zero this time, right?
Yeah, it would have been some finite value, right? Then there would have been some current.
Yeah, and VTH would have been some finite value as well. Like here you would go get
Yes,
3
yes.
volt and here you would get 2.5 volt.
So then VTH will be like
Be
0.5 volts.
0.5. So
Yeah.
0.5, and then your equivalent resistance would be like R by 2
It
and
will be R
R.
by 2, R by 2. Yeah.
Yeah, it would be R and this R.
R.
So your current would have been simply 0.5
Like
by
2R. Yeah.
yeah, yeah, yeah. So that's a nicer method actually. Mine is not that good, so that's a better method.
So like, so yeah, I solved it. This is some interview also I solved it like this. So yeah.
Yeah, okay, yeah. So that's a great and that's intuitive method as well. That has a better intuition. Yeah. So let's remove it off and move on to the next question.
Okay. Okay.
Okay. Now I will ask you a kind of different question. You can take your time in that. What should be the value of I naught here? Let's
Okay.
call these two transistors as identical, okay? And all transistors are identical in terms of Kn and everything like that, okay? Kn, K
GMs
plus.
and everything are yeah.
Yeah.
Okay. So like if this has 2 amps through it, so the VGs of these two are same, right? So VGs of these two are same. So from here, like 2 amps will flow, 2 microamps will flow. But in this bottom circuit, right, if VGs here also is same, so this one will try to flow 1 microamp through it. But like these two can't happen like at simultaneously. So
So there is one
something
more
like
condition, right? There is a condition for current mirror.
yes, yes, like the VDS of both of this should be also same. VSD and VDS should also be same for current mirror. Yes.
No,
So
actually, both of them
like
should be in saturation region, like, right?
yeah,
These two should
yeah,
be in
yeah.
saturation region.
So like yeah. So here, like if this is like not like equating, so hence some MOS has to be in linear, right? Some
Yeah.
MOS has to be linear and
Right.
another will be in saturation, right?
Yeah, yeah.
So like if I assume that like this is in saturation, so what will happen is like this 2 amp will get mirrored over here, and this 2
Okay.
amp will flow through this bottom MOS, right?
Okay.
But like here we know, like if this MOS is in saturation, the maximum current here is 1 micro, right? So like what will happen is so I think like we know we get the maximum current at saturation, but this MOS is like trying to put 2 amps through it. Wait, I'm not able to write. This MOS is trying to flow 2 amps through it. Sorry, 2 microamps through it. So I don't think it will like work. It will drive the 2 amps, 2 microamps.
Yeah.
So I think like this will be in saturation, right? So hence it will flow 1 microamp through it, and through this circuit also we will flow 1 microamp, and this will be in triode. Like, am I correct? Like, or
Yeah. Yeah. That's the approach only. Like this
okay,
has to go into the saturation and this has to go into triode.
yeah, because like this can't drive 2 amps through it, right?
Yeah. So like if this goes in triode and this goes in saturation, I naught goes to 1 microampere, and yes, this transistor can have 1 microampere. But if it goes into if this transistor goes into the saturation 1, then this transistor cannot have 2 microampere. So I naught would be 1 microampere, right?
Okay. Yeah.
Yeah.
Yeah. We can
So
move on to
was
that.
absolutely correct. Yeah, that was a good question.
Okay.
So let's move on to the next question.
Okay.
This would be an easy question for you, I guess. And yeah, this is
Okay.
based on
Sometimes easy questions become difficult in pressure situation actually. So this is for like our viewers also. Like some easy question will also become difficult. Just focus on like on your interview and stuff.
yeah. So this is the NMOS we are having. The input is increasing from 0 to VDD. Okay. You have to plot V
Okay.
naught versus V in. As I sweep V in, what should be the V naught value? Okay, take some
So
VT.
yeah, we assume some just some VT, right? Yeah.
So let's plot it here. Okay, because I can't see at
Okay. Fine. Yeah. This is VI. This is
let's
yeah.
assume some VT. So
Okay.
start typing.
So
Increase it from 0.
so at 0, right? So this gate voltage is at 0, and initially if you assume like everything is off, so the current through this is 0, right? So this output voltage will also become 0. So VGS is 0, but we don't have any VT, right? So this MOS will be off, right? So if you just keep on increasing this VG, the source voltage is still at 0. So at
Yes.
some point at like VT, this will turn on, right? This MOS will turn
Just
on.
about VT. Just about VT.
Just about to turn on. So the voltage here is 0. Now first we have to check like is it in saturation or triode. So if we check it, like the drain voltage is at VDD, and the gate voltage is like at only like VT only. So we know like for saturation VD should be wait, I'm not able to write. VDD should be greater than VG minus VT, so which is greater than 0. So VDD is greater than 0. This condition is true, right? So this is in saturation.
Yeah.
So if this is in saturation, so the current will slowly increase, right? Now if the current gets increased, we'll get some relation, something in like small signal analysis. We'll get like this current will be I equals to GM into VI minus V naught. So am I going in the right direction?
No need to write the equations and all. Like you just told that the current will increase. So the current can increase in like 3 parts, like this or like this or like this. Let's call this one as 1, this one as 2, and this one as 3. So what do you think will be the path? This is the linear one. This is also this
Okay.
is the parabolic one. This is also the parabolic one, right? So
Yeah.
correct one.
So like current the slope should keep on increasing for the current, right? Because it's a parabolic curve. So I
Yeah.
think this one will be the correct way with it. Like the slope is keeping on increasing here.
Yeah.
So here
Because
the slope is like going.
yeah. Because VG is getting increased, so slope keeps on increasing. Yeah, that's a good approach.
Yeah.
Or what you can tell is that like the V naught will increase, but not as much as V, right? V naught will increase lesser than V, right?
Yeah. Some value less than
Yeah. So like this, yeah. Your answer was fine as well. So initially we are in saturation region and the current starts increasing. So what happens after that? So let me make the diagram like this. So this is how we are going. So what happens after that?
So at some point, like this MOS will go into like linear region, right? Because at some point this VDD will be equals to VI minus VT. So at this point, so the input voltage will be, so it won't reach there because input voltage has to become VDD plus VT. So as we are not sweeping at that value, so it will keep on increasing. In our case, at some point, it will go to linear region, right?
But
Like
it
after.
can't. So
In
like
our case,
yeah. So look what I am saying is that like I am saying assuming it like at VDD we reach the saturation. Okay, I am saying that when Vn is equals to VDD, we are reaching the saturation region.
okay.
No, not the saturation region. We are reaching the saturation of V naught.
Yeah. Okay.
So what should be the saturation value? What should be the maximum value V naught can have? Like at VDD,
I think.
what can be the maximum value V naught can have?
I think it should be if it's VI, right? So if it's reaching that point for triode region, is it?
No, not in triode. At V in equals to VDD only. Okay, we are having the saturation voltage of output. That I am saying. Like
Okay.
V naught
Okay.
cannot increase above that
Go
voltage.
above VDD. Okay.
So
Okay.
what should be that value? What should be the maximum value that V naught can have?
So the maximum value V naught, is it like the supply voltage VDD? Is it?
No, this V naught. This
Because
V naught.
okay, this VDD. Oh, V naught.
V
Sorry.
is equals to VDD now. Okay, and I am saying that V naught has reached its maximum value. So what should be that value?
So okay, so if it's at maximum value, so it has to turn on, right? So VDD minus V naught should be equals to VT, right? Because it
Yeah,
has to be more than the threshold voltage.
yeah, yeah.
So V naught should be equals to VDD minus VT.
VT. Yeah, yeah.
Maximum
VT.
voltage. Yeah.
Yeah. Okay. So yeah, it should be VDD minus VT. Yeah, yeah. That's correct. Yeah. So let's move on to the next question. Okay, the meeting got over in between, so yeah, we are restarting it. So let's move on to the next question. So I guess you must have seen this circuit before, like just asking you if you know it already or not. This is R, this is C, this is V in. This is, can I undo it? Yeah, this is one R as well. This is R as well. This is R as well. And let's make it ground for now.
Okay.
What is that?
So if you do like the analysis, right, for zero and high frequency, so at zero, like this cap is getting open circuit for like zero frequency. So no current is flowing through here. So the whole VI will get transferred through here, right? So this VI will get transferred to here as this op amp is in negative feedback. So virtual short will happen. So if we
We will have some
apply
finite gain.
KVL in this, yeah,
And we will have some finite gain. Yeah.
yeah, we'll have some finite gain. Yeah, we'll have some finite gain. Yes.
Okay.
Now for like infinity, right? For S equals to infinity, this cap will go in short circuit. So this inverting terminal will come at to 0 volts. So where it's 0 volts, so the current through this is 0 amps. So VO will be 0 amps will be flowing through here. So VO will be equal to 0 here. So at infinite frequency, we're getting 0 gain, and at 0 DC frequency, we're getting infinite. So I think it will be something like low pass filter. Is it?
Okay. Yeah. So it will be a low pass filter. Now what I am doing is that I am removing that ground. Just I am removing this ground, and let's remove it off. Just clear it from your
Yes.
side.
Okay, okay, yeah, I'm clearing everything from my side. Yeah.
And I'm putting one more V in here. The input is the same. Okay.
Sorry, can you just redraw it? Yeah.
Yeah, yeah. Okay, it's fine. It's fine. The input is the same at both of the terminal. I have the same input. So now what kind of filter is that?
Okay, like for DC analysis, like same similar type of analysis happens. So this VI comes over here. Now both of this end has VI, right? So the current through this is 0 amps. Uh, Current through op amp is 0, hence the current through this is 0 amps. So the drop across this R is 0. So at DC frequency, V naught will be equals to VI.
Yeah.
Okay.
Okay.
Now at infinite frequency, what is happening? Like this is getting virtual short. So this will become 0 volts. So if this is 0 volts, so V naught will be equals to basically minus VI if you apply like the KCL at that non-inverting node, right?
Okay.
So I think it can be like it can be all pass filter or it can be a band stop filter, right?
Yeah.
Because we are getting gains at both of the spectrums, both of the end of the spectrums. It can be either of those.
Yeah. So it's a standard circuit. I guess you know it
Yeah,
already.
yeah, it's basically a all pass filter. Yeah.
Yeah. So let's analyze it. Now tell me the location of pole for this one. Location of pole
Okay.
for this
So
circuit.
pole
Can you
for
tell
this
me?
one, if we like find the R equivalent from this end, right?
Yeah.
We have to short this VI, right? Now no current is flowing through here, only like we're seeing one R. So the pole will be minus 1 by RC. for this like circuit.
Okay. So now you know the pole. Okay. And you also know it's a first order circuit, right? You know it's a
Yeah.
first order circuit. You know the location of pole. You know the DC gain, right? You know the gain at infinite frequency. So by using these information, can you tell me the location of zero?
Okay. So
So will there
like
be a finite zero or not? Like first tell me, will there be a finite zero or the zero will be at
uh
infinite?
so if I make like this cap like short circuit,
Yeah,
now if I see like are we getting any output or not through
yeah,
this cap, charge through this cap is zero.
yeah.
So uh wait second, charge through this cap is zero, so this will be 0 volts here. Yeah, we are
Yeah,
getting some finite gain at the output, right?
yeah.
We are with minus vi. So yeah, this cap will like give some zero at the output, right?
Okay,
So
good.
there will be some finite zero.
Okay, good. Now, what should be
Okay.
the location?
So like we know the like this is a first order, so like it has some 1 plus s by omega z and 1 plus
Okay,
s by omega p. Omega p we already know, like this is minus 1 by rc. So uh this will be basically sorry if I just rub it, uh, this will be rc, right?
yeah,
And we already know like at s equals to 0 the dc gain is basically 1 for this one, right? So we have the dc gain. So if we like calculate for s equal to infinity, so we know it should be coming out to be minus 1, right?
okay,
So if I like put s equal to infinity in this both of these cases, so the coefficient of s terms will only remain, so this will be omega z uh, divided by so rc should be equal to minus 1.
okay.
So this omega z equals to minus 1 by rc. So I think this should be the 0, right?
Yeah, great, great, great. So now you can write the transfer function. So the transfer function would be omega RC, no, sorry, SRC, 1 minus SRC actually, 1 minus SRC upon 1 plus SRC, right?
That's, yeah,
So
yeah,
from here you can tell what kind of filter is that.
yeah. It is a all pass filter because it has like
Okay.
symmetrical pole 0.
Yeah, okay, great. So let me check if I have some more questions or not. Yeah, this is a standard circuit. I can ask you that question as well. So, so you will tell me what this circuit is called, like where it is used, or just the analysis part. You will tell me. Let's give it some V bias. And, V in by 2 I am applying here, and minus V in by 2 I am applying here. And, I'm collecting my output here. Okay, and let's call them M2 and let's call them M1. Can you tell me the differential gain V naught by V in? V naught by V in value you need to tell me. Can you tell me that?
Okay, so this is basically like the differential amplifier for when you are taking the single ended output. Like
Okay, yeah,
this is basically the standard circuit. Okay, uh, so the differential gain, right? So first, like for differential gain, we are already applying vi by 2 minus vi by 2. So what will happen is like what happens in this is this becomes ground for this, right? Because like no current flows through this end, uh, because if you equate this like this has you want me to prove it, or like just we should go
no,
ahead with
okay,
this.
like can you tell me intuitively why this potential goes to zero?
So like here if you assume some potential V, right? So from here some current will flow GM VI VI by 2 minus
Forget that. Okay, that's fine. But just the intuitions. Like, what if I increase V in by 2? Yeah. What if I increase it? What happens?
So if I increase V in by 2 from here, right? So the current through this will get increased, right? GM V in by 2.
No, what happens
So
to
this
this node? This. If I increase V by 2 here, what happens to this node?
so
This node
this
increases
node
or
will
decreases?
this node will also try to increase, right?
Yeah, right. So if I am increasing here, what will happen here? It will get decreased, right?
Yeah,
So
this current will increase.
so this will also try to decrease. So both are nullifying their effect. So this goes to 0, right?
Yeah, like that also. Yeah,
Yeah.
we can prove it like that also. Yeah.
Yeah. Or you can write the equation as well. That is
Yeah, we
also.
can write the equation. So only one
Yeah.
voltage will come up. So it will
Yeah.
be
Yeah.
0
Okay,
only.
that's fine.
Solution.
Now just try to calculate the gain V naught by V.
Okay. Okay. So as this potential is 0, right? So this current will be GM1 VI by 2 from this. So this current will also be through the MOS M2 GM1 VI by 2. Now as this is current mirror, right? So this current will also be GM1 VI by 2. Now for calculating the gain, basically what we do is we like sort the output for calculating the trans conductance, right? Overall trans conductance of the circuit. If we sort the output, then and if we find the ISC through this, the short circuit current through this. Now the relation something is like this: ISC is equal to overall GM into Vn, right? Now here from here we'll be able to find the GM. So
Okay.
the current through this
GMR
is
out method
GM1
you are
VI.
using. GMR out
Yeah,
method
I'm
you are
using the GMR road method. Yeah, I'm using the GMR road method. Yes.
Okay.
So so the current through this is GM1 VI by 2. So here also some current will flow, which is GM1 VI by 2, because this is negative sign, right? So the current will be in opposite direction. Hence, two currents are here adding up to ISC. So the overall current will be GM1 VI, and this is overall GM. So and sorry, what is it? This is the ISC. Sorry, this is the ISC, right?
Yeah.
This is the ISC. If I write this is the ISC, right? So basically ISC by VI is equal to GM1. The overall GM is GM1. Now, like for calculating the R out, what will happen is, so we are assuming like channel modulation. So this has some RO, and this also has some RO, right? RO2 and RO1, and this is ground, right? And now as this is current mirror, so this becomes open circuit. This M2 MOS becomes open circuit, current through is 0. Hence this also becomes open circuit. The circuit at the left totally detaches. So hence at this point, this RO1 and RO2 are both in parallel, right? So basically the equivalent R out will be
Yeah,
RO1
so
parallel
this
with
is how,
RO2.
like, now I get it. Yeah. RO1 parallel with RO2. This is your gain, right?
Yeah.
So you made an assumption here when you were writing the current, like these are very high, so the current would not go into
Yeah,
these
yeah,
two.
yes. Like we made the like that was in the approximation. Then else
So it's
like
a
it would be
very
a bit
high gain,
difficult.
and from that we can make the op-amp, single stage op-amp. That's how we make the single stage op-amp, right?
Yes. This is basically
And
the
that's just a common source amplifier we will make here, and we will get the op-amp. That's the basic idea, right? So
yes.
yeah. So that's it from my side. Yeah, the interview went really well, and it was completely expected from you. Like this interview was not like just to like I wasn't testing him. I know like he's good enough because he's already working in TI only. So just that like you would get to know how to approach a question, how to answer a question. Like if these kind of questions are asked in your interview, so how one should approach. So that's why we arranged this interview. And one more thing is that like I have also given the interview in his channel. Okay, I will put the link of that. Then you can go to his channel and watch my interview. Also, there are many content there. He also makes some content, so that also you can watch. So in like you will see both of us interviewing and getting interviewed. So that will help you in your preparation, I guess. Yeah, and also you can opt for mock interview as well. I will put the link in the description and comment box, so you can opt for mock interview as well. Okay. Yeah. So Anish, anything you want to tell?
Yeah, the only thing is like it's okay to stutter and it's okay to like say wrong. The interviewer will tell you like guide you in the right direction. You just have to like focus a bit. Like have to take the hints. That's really important. Take the hints of the interviewer, right?
Yeah. Yeah. Okay then.
That's it from. Yeah. Okay.
Yeah. Okay.
Thank you. Yeah.